numero uno, dy dx would be what? 15x squared times e to the 5x cubed. All right, so exponential base e, generally the idea is that you're going to keep one part of it as is in your derivative, and then the other part would be the derivative of the exponent itself. So the derivative of 5x cubed would be 15x squared. All right. Same idea for the sine function, the sine of e to the 2x plus 1. We have e to the 2x plus 1. That part's going to work out exactly the same. We do have the sine function to contend with. If we're applying the chain rule here, now everything from here on out is going to be some variation of the chain rule. It's just a question of whether it's the chain rule involving just an exponential function, or is it, exponential function within like a sine function or a log function or something like that. All right. So derivative of the outer function becomes cosine of my inner function. I'm about to make my parentheses too small. Times the derivative of the inner function, which would be e to the 2x plus 1 times 2. The derivative of the exponent. Because derivative of 2x plus 1 would be 2. That would be, this guy becomes that. All right. Number 3, we're looking at, and that concept repeats itself over and over again, so we'll see it again in action right away. We're looking at the product of two functions, so a product rule situation. So dy dx, first function, e to the 3x, times the derivative of the second function. All right, so function within a function. Derivative of cosine is negative sine of e to the x, multiplied by the derivative of the inner function, which would be e to the x. So that's first times the derivative of the second, plus the second function times the derivative of the first. Second function would be cosine e to the x, times the derivative of the first, which would be e to the 3x times 3. But I'm going to write that as 3e to the 3x. All right. So all of that together represents the derivative. And I just wrote it in 2 lines for space considerations. Number 4 is a quotient rule situation. All right, so a little low D high, high D low business. So I'm sure I mentioned this at some point, that I like to take care of the denominator squared part first, just in case, because odds are if I'm going to forget something, that's probably what I'm going to forget. So low D high, e to the 2x times 2, so 2e to the 2x, minus the high, e to the 2x, d low. All right, so d low would be, well, the 1's going away, right? So it would really just be the same as the derivative of the top, but you can find the derivative in and of itself anyway. So that would be 2e to the 2x. So these exponential situations, they end up being a little bit more simplifiable. In the case of 1 and 2, not really worth it too much to do anything with that. Because, the best I can do is rearrange some things. I already rearranged number 1. Number 2, maybe I just move these two factors to the front. But in 3 and 4, I have a common e to the 3x that can be factored out. It's just I didn't do it because it's not going to advance the cause. All right? But in number 4, I also have a common factor, 2e to the 2x, that could be pulled out. And when I do that, it actually does advance the cause. All right, so if you were going to practice simplifying something, it's probably something like number 4, because again, you don't know. I mean, you do know something is going to end up on a test as a multiple choice question, but trying to predict what kind of question would be the one that you'd have to simplify, maybe not as clear in the early goings, but as you get more and more experience, you start to see what's more and more likely to be a multiple choice type question. All right, so if this were multiple choice, odds are that's not going to be one of the choices. Let me factor out 2e to the 2x. You see that we have 1 plus e to the 2x minus e to the 2x. Those two terms will then cancel. So your entire numerator cleans up very nicely to just a 2e to the 2x. And now we have a derivative that's a little bit simpler. I mean, it's definitely visually a lot simpler than what we started with. But in terms of the math behind it, I don't know. It depends on what you're looking for. If I needed to find the second derivative, much simpler to work with this. If I needed to substitute, I don't know that it makes a difference. Like if it says, find the slope when x is equal to 0, I mean, I think I can just as easily put a 0 in for x here as I can here. Anywhere I put a 0 in, the e terms are going to go to 1, so the calculations aren't going to be that complicated either way. Right? But here, if I needed to find a horizontal tangent or a vertical tangent, then this is definitely going to be the way to go. Second derivative, things like that. So there's value in knowing how to simplify it. Very rarely, I mean, at least I can't even think of a situation off the top of my head where you'd want to distribute out the bottom of the quotient rule derivative. So that's already in factor form, so leave that as is. If anything, you want to clean up the top. The big misconception that people have, and it's a huge misconception, is that they think the way to do that would be to distribute out the top. Sometimes that works. The better way to go is to find a common factor from within each part of the top and pull it out and then collapse down whatever remains. All right. If you're going to get something to cancel, that's probably where it's coming from. All right. That's the biggest piece of advice I can give for something like that. That was extraordinary. I mean, if I didn't understand it before that explanation, I understand it now. I mean, that's how good that explanation was. It was beautiful. Yeah, I know. It's great. So anyway, number 5, sine cubed. All right, secant cubed. So now that I gave that wonderful explanation, I'll immediately screw up something completely. That's my MO. At least think of it this way, so then it becomes clear or clearer how the chain rule is going to take effect here. So it's something to the third power, so 3 times that something to the second power. Then I need the derivative of the something. So this guy I have to differentiate. So the derivative of the something. Well, the derivative of secant under normal circumstances. So secant of something would have the derivative equal to secant times tangent of whatever is contained within the secant function. So we're looking at secant tan of that e to the 4x then I just need to multiply by the derivative of the e to the 4x, which would be 4e to the 4x. And it's all like squished in now because I didn't take note of how much space I had available. Told you I'd mess something up. But if I increase the size enough, nobody can see that it's uncomfortably close to the solution to the previous question. But yeah, so in terms of structure, this is probably as ugly as it gets. If you had to do it out, like with Y's, U's, and even V's, you know, the elongated approach, it's a little messier. But if you have an organized approach, like a mental structure, then it ends up being a little bit easier. I would say, or at least this is the way I do it, and it's weird, but it works for me. I talk to myself. Like that's something to the third power. Like I'm actually saying that to myself. Like most of the time in my mind, but sometimes it comes out. So like when I'm working on a problem, I'm like, all right, I got something to the fourth power. That's 4 times that's something to the third. Derivative of the something is secant times 10, and so on. So it works for me. It's not going to work for everyone. It definitely isn't going to work during a test. So be careful, but you know, having a conversation with yourself isn't always a sign of insanity.